Measuring the quality of a survey. Using accuracy and precision to measure the quality of a survey. Describe the important features of a sampling distribution, including the standard error. Evaluating surveys. Statisticians evaluate the method used for a survey, not the outcome of a single survey. For example, if a group of researchers were to survey 1,000 randomly selected people, we would expect the results to vary from sample to sample. Because we would want to know how the group did as a whole, we evaluate the estimation methods, not the individual estimates. Okay, how the data was collected. An estimation method should both be accurate and precise. Accurate, the method measures what it was intended, correctly estimates the population parameter. Precise, if it's repeated, the estimates are very consistent. Accuracy and precision. If the goal is to get the golf ball in the hole, which of these pictures shows a method that is accurate and precise? So starting from the right, it shows that it's accurate in the vicinity of, but it's not very precise. Looking at the middle one here, it shows precision, close together, but not a lot of accuracy. It missed the hole. This one here, the first one, is accurate. You replicate it, you get the same, close to the same result, and it is precise. It does what it's supposed to do. So you can see it there. Understanding the behavior of estimators. Simulation 1 here. They have a population of 8 people, two cat people and 6 are dog people. Random samples of 4 are taken from the population, and the percentage of cat people are noted for each sample. So looking at the percentage of cat people. So how many do we have here? 2, 6, 8. So the population is 25% cat people. Which sample will contain 25% cat people? It's possible to get a sample with 0% cat people. Let's find out. In this case here, looking at the sample, random samples were taken. So you can have a sample that is random but not be representative of the population. They pick randomly, pick 4, 0 cat people. This one here is 25%, 25%. So it is possible just picking randomly to get a sample that's not particularly representative of the population. The sample proportion here changes from sample to sample, but the population sample remains the same, because we already know that it's given. It's the status quo, 25% cat people, but from the different samples we pick, we could get anything. And also, depending on the size of the sample, it can change that too, that percentage. The probability distribution of A p hat here is called the sampling distribution, the probability distribution of a sample. It's called the sampling distribution here. You can represent it using a table or graph. Probability of getting 0 cat people here. And then the probability of it. The probability of getting 25% cat people here. Okay. And the probability of seeing a 50% cat people is here. All this is from the sample proportion. I didn't say anything about the type of size of the sample here. These are all the possibilities that can happen. Our estimator p hat is not always the same as our parameter. The mean of the sampling distribution is 25%. Okay, the same as the value of p indicates that the estimator is unbiased. So when you can get if you have a sample, if you choose a sample, and the sample represents the population, it's an unbiased sample. You have a really good random sample here. Then it's a good representative of the population here. Even though p hat is not always equal to p, the estimate is never more than 25 percentage points away from p. Okay. The standard error in this is the standard deviation of the sampling distribution. It measures how much an estimator typically varies from sample to sample. So if you have a population, let's say I have a population of adult males with heights, and I want to do the average height. The standard error is simply the deviation between the different samples, how much it varies from sample to sample. And the goal here is to have a standard error that is small. We say that it's precise, which means that every time I reach in and grab 5 people, I get this close to the same value being measured. Simulation 2. This time we consider a population of 1,000 people, 250 of whom are cat people. 25% of the population. We take a random samples of size 10 and find the sample proportion, p hat, of cat people. Using technology, 10,000 samples were taken and the results are here. So 10,000 samples were taken here of size 10. So they did 10,000. They took 10,000 samples here, looking at the data here. And notice it's somewhat of a spread, and it's centered around 25%. We already know that there's going to be at least 25% cat people, and the samples will bear that out. For the most part, the samples will bear that out. You may have a few samples here that weren't either too high or too low. Since the center of the distribution is about 25%, the bias of p hat is still 0, even though a larger population sample was still used. The variation of p hat is less. This estimator is more precise than even though the population is larger. In general, precision has nothing to do with the size of the population, only with the size of the sample. You increase the size of the sample will become more precise, meaning that every time I reach into it, I get the same thing out. I get the same thing out. I get the same thing out when you increase the size of the sample. Again, we consider a population of 1,000 people, 250 are cat people. In this case, they increase the sample size from 10 to 100 to take 10,000 such samples. From 10 to 100. So now they're doing 100 people, and they do 10,000 such samples. So let's take a look at what happens with simulation. So when they notice they increase the sample size here, so now the data is more precise here. Almost a perfect normal curve. Looking at 10,000 samples, each one has 100 elements in it. So the estimation method remains unbiased. Unbiased center is still at 25%, the population proportion. The shape of the histogram looks more symmetric than one of the 4 samples of size 10. The estimate is more precise because it takes a larger sample size here. Okay. The standard error is smaller than for samples of size 10. So the larger the sample size, the standard error gets smaller. What's happening is that when you do a larger sample size, you have a larger sample size that's more representative of the population. So the sample mean, the p-hat, will correspond more closely to p when you increase the sample size. The estimator p is unbiased for all sample sizes. As long as we take random samples, the precision improves as the sample size gets larger. If you notice that as you increase the sampling, the shape of the distribution is more symmetric for larger sample sizes. See right there, bolded. Increasing the sample size improves the precision. Find the bias in the standard error. The bias of p-hat is 0. Standard error of p-hat here. So you can see that p-hat here is the estimator. Gives us kind of the an estimator for the mean for that sample, and the standard error is like a standard deviation for that sample. An estimator for the standard deviation here. Now you can use this formula here when the sample is randomly selected from the population of interest. If the sampling is without replacement, population must be 10 times larger than the sample size. Okay.